Okay, class, where we are now, we want to talk about the renal corpuscle filter. The renal corpuscle filter. What did we say the renal corpuscle consists of? The glomerulus and Bowman's capsule. The glomerulus and Bowman's capsule. Now, the filter basically is this. The blood needs to be filtered of waste, but the filter should not let out big things and negatively charged things. The only thing should go into the filter is something that's 3 nanometers or less in diameter. Now you say, what's 3 nanometers or less? That would primarily be, let's see what we have here, water, electrolytes, glucose, amino acids, small proteins, urea, uric acid, creatinine, and others. So that's what should end up going through completely through all the layers of the filter. What should be held back? All the cells, formed elements, and the proteins, particularly the large and medium-sized proteins. Other stuff can essentially go through the filter. So now with that in mind, let's look at what are the layers of the filter. Let's look at what are the layers between the inside, the lumen of the capillary, all the way into Bowman space. The lumen of the capillary all the way into Bowman space. And the flow is going from the lumen of the capillary through all these layers there. All right? So let's see what we have there. All right. So we go here. The first thing is, going back to blood vessels, the capillaries of the glomerulus are fenestrated. Now remember what we had, we had continuous capillaries, fenestrated capillaries, and what? Sinusoidal. These are fenestrated, which means a little narrow window. The window is about 70 to 90 nanometers. So you can't get through the capillary endothelial cells if you are the formed elements. So that would kind of keep the formed elements out. Now, however, some of the formed elements can do a little diapedesis. Remember, a few can perform diapedesis. They could squeeze through. You may find a few WBCs. You shouldn't find any red blood cells through the normal filter. All right. Then what's underneath an endothelial cell? A basal lamina. The basal lamina has about a 300 nanometer thickness, and we'll just get to the bottom line. It's the chemicals in the basal lamina are negatively charged. Now, what would that do? Impede negatively charged particles from going through the filter. What particles are negatively charged? Most of the plasma proteins, the albumins, the globulins, and the fibrinogen. All right, so that would do that for them, the basal lamina. All right, now we get to the fancy stuff. All right, the capillaries are the visceral layer of Bowman's capsule is lined by some cells that look like feet and toes. And those particular cells are called podocytes. So the lining cells of right here, of the visceral layer of Bowman's capsule is consisted of these podocytes. These podocytes have these primary pedicles and secondary pedicles. Primary pedicles coming off and secondary. And they are wrapping all around those blood vessels. Just like that there. So when you see a picture like this side, they're trying to show you the wrapping of the podocytes, and this side without it. So those podocytes are wrapping around there. Okay, keep that in mind. They're tight down. They're squeezing on that capillary. So here's another picture of it right here. See how they are? All right. So when you see that, then the spaces between the podocyte toes, I'm going to call, podocyte toes, since they call them foot cells, are called the filtration slips. They're about 20 to 40 nanometers wide, and therefore they keep some of the smaller stuff out. Now, between here, right there, these filtration slits, they're actually covered by something we call a slit membrane. A slit membrane. So between there, you kind of have this slit membrane that you see here. Slit membrane. Or also called a slit diaphragm. Right between the fingers. It would almost look like webbing between your toes. Alright. And that's about 6 nanometers thick. But that webbing has circular pores in it. So that webbing has circular pores in it that are about 3 to 5 nanometers wide. So anything that's less than 3 nanometers could get through. Anything what? Less than 3 nanometers could get through. Once you go through, because now you're in Bowman space. See, now you're in Bowman space. So what did we say could get through then? Water, electrolytes, glucose, amino acids, small proteins, and things of this nature. So that's what would arrive essentially within Bowman space. That's what would arrive in Bowman space. Okay? All right. So, the principles of fluid dynamics. The glomerulus is more efficient than other capillary beds because its filtration is more permeable. Blood pressure is high. Now, let's talk on this blood pressure being high. Okay? What I want to show you is that you've got a 2 arterial process. Arterial capillary. Okay. That means you could create a tremendous amount of back pressure. Let me tell you what I mean. You could get a higher pressure in these capillaries. I want you to think about this with me. Because if the efferent arteriole was to constrict down somewhat, and in most cases, unlike this picture, the efferent arteriole is generally narrower than the afferent. Now, what would that do? Create a back pressure. Think about the term resistance, the radius. Create a back pressure. That means that back pressure would force or increase pressure in these glomerular capillaries, facilitating filtration, facilitating pushing fluid out. Because you have a 2 arterial system, this right here could narrow down, creating a back pressure, i.e. increase in resistance, which would push the fluid out. Now, the question would come, well, we always said you never wanted to put too much pressure in the capillary. They were thin, they would blow out. Why can you do it here? Because, we go back, these podocyte fingers and toes wrap around it. So they add extra reinforcement. See, the other capillaries in your body don't have a wrapping like this. That means they could expand and blow out. But by these having a wrapping, it gives more fortification to the capillary, and it could tolerate a higher pressure. It could tolerate what? A higher pressure. So the filtration membrane is permeable, okay? Which means that, because see, you have the fenestrated capillaries. See, fenestrated capillaries are very permeable. Remember, the normal capillaries in most of the body were the continuous. They were not quite as permeable. The glomerular blood pressure is high. Why? Because I just explained that efferent or afferent arteriolar advantage to be able to push the fluid out, right? So it has a higher net filtration pressure. Remember the net filtration pressure we talked heavily about in the blood vessel chapter. Okay. So that's kind of what we're looking at. All right. So that would be this here. So then when we look at that net filtration pressure, here's the formula. I don't think I have to go through it. All you have to do is go back and look at the blood vessel chapter. No use of being redundant. But we're saying the usual pressure in most capillaries, net filtration pressure of 10, but the usual pressure in most capillaries, go back and study, is 35 millimeters of mercury pressure. I put this right down here for you to see it. Go back to that chapter. The usual is 35, but in the kidney is 55. Why could it be so high? Well, the reason it wants to be high is to push the fluid out. But the reason it can be so high and not blow out the capillaries, where it would have if it was that high, let's say in a capillary in your skin, is because those capillaries are being wrapped by these podocytes, and by doing that, that fortifies that. So you can see here. See, that's what we had in the blood vessel chapter. That's what we had in the blood vessel chapter. But this would be the one that we have here, 55. You can look at the picture. And the reason is those podocytes are really holding tight on that. Okay. So you can easily look at that. See, here's my, but I'm not going to get into this because you've already studied this. So you can do that on your own. No use of being redundant in these films. But I put it there so you can study it. Okay. Afferent and efferent arterioles offer high resistance to blood flow. Blood pressure declines from 95, and you can see there the reason, the two arteriole anatomy, which we just talked about. Okay. Resistant in afferent arterioles. See, it protects glomeruli from fluctuation of systemic pressure. See, in other words, right here, let me just kind of explain this and you can read on it. If your blood pressure gets too low, remember you're starting about a mean arterial pressure out of the heart, coming at 100, and then by the time you would have gotten down to here, by the time you would have gotten here, you'd be about a 55 based upon all the different resistors. All right. Now, let me show you something. Oh, you have a 55. Okay. If I go to the calculation here, to get a 10, a push-out force of 10, which you see here, I have an opposition force of 45. So you gotta be about a 55 to get that 10. Now just think about this now. You gotta be a 55 to get this 10 because you have an opposition force here that's pushing you back in like that there. That's opposition. Capsular hydrostatic pressure, that's pushing you back in. Okay. So you got that. And you got the blood colloidal osmotic pressure trying to hold you in. So you got the blood proteins trying to hold you in. Remember, you had a hold-in force and a push-in force. A hold-in force, that was the osmotic pressure of the blood holding a suction, and this here. So what you need is to have, you need to have a 10. You need to at least have a 55 in order not to perfuse the kidneys. So if the blood pressure drops too low as you come down, you wouldn't have a 55. And the lower you get, the less of this you're going to get. And if the blood pressure gets too low, like a 60, a mean arterial coming out of the heart or lower, you won't have enough to do the kidneys, and the kidneys will dry out and you'll lose your kidneys. That's part of that shock deal. That's part of that shock deal. So I want you to think on that. We're going to close right here though.